Okay, everybody, so let's get started. So once again, for those of you who have joined us, welcome to everyone. Good morning, good afternoon, good evening, wherever you are in the world. Welcome to this virtual training course for Python for high performance computing. Obviously, we would have loved to have had you in Lugano, had the circumstances been different, but yeah. This is kind of the new normal that we have to deal with at the moment, and we need to adapt. And first of all, I hope that your friends and family are safe and well. Perhaps the positive aspect is that some of you can attend this course that maybe we're not able to attend otherwise. So for example, if you could not travel, or if you didn't have any budget to travel, or perhaps it's just too far to come to Lugano. So it's great to have you here. Indeed, looking at the list of participants, we have people from as far away as the United States, Canada, China, India, and Australia, along with many people from Europe, so including Austria, Italy, the Netherlands, France, the UK, Belgium, and of course Switzerland. So welcome to all of you. A few details about the webinar format. So you all have your microphones muted at the moment. If you want to ask a question, there's a Q&A box, so you can put your question in there, and either the person who is speaking will answer the question directly during the presentation, or someone, one of my colleagues, will answer in the chat, or we can answer all together at the end of the session. So don't be afraid that your microphone is on. It's not on unless we activate it for you, and if you want to speak, and if you want to show your video when you're asking questions later in the day, then that's no problem at all. Just let us know. I think that there will be a show of hand or some kind of functionality where you can wave, or you can give a thumbs up or something like that. If people can look for that. Yes, so Manjeet has raised his hand. Thank you very much. And likewise the others. So it's probably you'll be able to find that somewhere. And maybe it just gives us a little bit of acknowledgement that you can hear what we're saying. Thanks, everyone. So the course was fully subscribed within a few days of advertising it. So I guess that speaks to the popularity of Python. Maybe it also tells the tale that people need to learn some tools and techniques in terms of extracting good performance from Python. There are some obvious, I guess, features of Python that are kind of problematic when it comes to performance. First of all, it's an interpreted language. So yeah, and it's dynamically typed, things that are difficult for performance reasons. I guess people that have been working in HPC for a long time know that you need to give the compiler the chance to produce optimized code for you. And if it's a interpreted language, then it really puts the onus on the language and your ability to write good code in order to get good performance. And you can't just rely on the compiler to produce good machine code for you. There's the famous GIL or GIL, the global interpreter lock. And this basically prevents multiple threads from executing Python code at the same time. So that's another thing which is potentially a performance difficulty or bottleneck. However, during this course, we'll see various ways that you can get around this GIL. For example, NumPy arrays, you can get around it, or if you're calling C through Python, things like that. So we've got 3 days of content. It will expose you to a number of different techniques and tools for making use of both GPUs and CPUs in a performant way. Of course, at CSCS, we have a large GPU-based machine, Piz Daint, roughly 5,000 nodes, each with one Intel Haswell socket and one NVIDIA P100 Tesla-based GPU. And twice a year, we have these top 500 list published at the 2 major HPC conferences in the world, ISC in Germany and Supercomputing in the United States. And if you had seen ISC a couple of weeks ago, they released the most recent top 500 list, and Piz Daint is still in the top 10 at position number 10. It slipped down a few places, but still one of the biggest computers in the world, and you will of course get to use it for exercises over these 3 days. The course will be taught by 4 members of CSCS. First of all, Rafael, he has basically put the course together. He has a PhD in physics from University of Lyon, where he worked on ab initio calculation and predicting crystal structures. He then moved to University of Basel, where he worked on the machine learning, using machine learning to predict chemical properties. He has been at CSCS in Compute and Data Services team since 2017. And then we have Theo, and he has a master's in finite element analysis and a PhD in civil engineering and computational mechanics from the National Technical University of Athens. He also joined CSCS in 2017, I think. We then have Vasilius. He has a diploma in computer and electrical engineering and a PhD in computer science, also from National Technical University of Athens. He leads the scientific computing support group at CSCS, and he's also the lead developer of Reframe, which is a regression testing framework specifically designed for high-performance computing systems. And there's me, Tim. I've been at CSCS for more than 10 years. I have a background in theoretical chemistry, but at CSCS, I manage the Jupyter Hub service. Jupyter Hub is basically a tool that allows you to use Jupyter notebooks in a multi-user environment. So it deals with things like authentication and spawning your notebooks on big machines. So many of you have probably used Jupyter notebooks or Jupyter Lab in your work with Python, and we will use Jupyter Hub tool to be able to use notebooks on Piz Daint, our flagship machine. And then you'll also will have had contact from Guilherme Peretti-Pezzi, probably by email, and you'll also see him in the list of panelists. So he leads the Compute and Data Services group here, and he helps coordinate the training program at CSCS. He has a PhD in computer science and also more than 10 years experience in high performance computing. So let's look at the agenda. The important things to note are that every day we start at 9 o'clock in the morning Central European summertime, so i.e. 15 minutes ago, and every day we finish at 4 p.m. 1600 CEST, which is 7 hours from now. We will have the lunch break every day at midday for 1 hour, and then we will also have a break in the morning and a break in the afternoon of 15 minutes. In terms of today, what we're going to start with is a bit of a hands-on session to get you up and running on the machines. I will give a sort of 1 hour tutorial on the use of Jupyter Lab. And as I say, we'll be using Jupyter notebooks throughout the 3 days. So if you haven't used Jupyter, then it will be a good chance to learn the tool. And maybe you have used Jupyter, but not Jupyter Lab. And so even if you've used Jupyter Lab a lot, maybe you'll learn something. We'll have a break, and then we'll get into the more heavy stuff. Rafael will talk about Python packaging and environments, and then get into vectorization using NumPy and SciPy stacks. After lunch, we'll talk about some profiling and memory management, and we'll have the first part of Numba. So Numba is a just-in-time compiler for numerical functions in Python, and Numba can be used both for CPUs and GPUs. This part will focus on the CPUs, and later in the week we'll focus on GPUs. In the rest of the afternoon, we'll introduce Dask. So Dask is a way to scale Python. The idea is that you can run the same kind of Python code on your laptop and then scale through to a cluster or a supercomputer. It's good for both generic parallelizable code, but it also has, you can use the familiar APIs from NumPy and pandas, for example. So you can do array-like operations on NumPy arrays, and you can do data frame type operations on your pandas frames. The idea is if you have, for example, a NumPy array which is too big to fit in the memory of your laptop, then you can use Dask to be able to still work on that in a kind of familiar way, a very NumPy-like way. But it will manage all the memory for you, so you can continue to work. Tomorrow, Theo will continue with Numba, second part, and then introduce Python. Python is basically an optimizing compiler for Python, along with some clever extensions. And then Rafael will be back to talk about F2Py, which is a Fortran to Python interface generator, and CFFI, which is the C foreign function interface for Python, basically allowing you to interact with C code directly from Python. And then we'll have a 1 hour Q&A session, so you can ask questions in depth about any of the topics that we've discussed on the first couple of days. Then on the last day, Vasilius will talk about Numba, specifically for GPU code, in a couple of sessions in the morning. And then after lunch, Theo will talk about CuPy, which is again a NumPy-like API, this time for producing CUDA code that can run on NVIDIA GPUs. Then finally, I will introduce how to go beyond single node computations. So we'll talk about using MPI for Pi, which is an MPI interface and bindings for Python, and how you can use that in a notebook using IPyParallel. And then from 3 o'clock till 4 o'clock, we'll look at some conclusions and again have plenty of time for Q&A. So without further ado, I think we should get going. You should have received some login details either from Rafael or from Guilherme, and you can open a browser. Would prefer if you use Firefox or Chrome, and we offer no guarantees for Internet Explorer and Safari, depending on the exact version, and operating system might also not work. So we definitely recommend Firefox or Chrome, and visit https://jupyter.cscs.ch. And I will switch now from sharing the slide to sharing a browser. Okay, so hopefully you can all see that. Maybe give a thumbs up if you can access Jupyter.cscs.ch. Thanks to everyone who's doing that. And what we're going to do is we're just going to get a single node. The Jupyter is going to launch a notebook for you on a compute node of our big machine, Piz Daint. So you'll get access to a dedicated node with dedicated CPU and dedicated GPU. What we're going to do is, what I would suggest first of all is that you ask for a decent amount of a duration. So let's go with 8 hours. Otherwise, your notebook will stop working at some point, and then you'll need to relaunch again, and maybe it will be a bit of a hassle. And then we will go to advanced options. And the thing that you need to enter here is the name of the advanced reservation. And so it should be HPC_Python. Please mention in the chat if you're unable to first log in. So you will need to, when you first go to jupyter.cscs.ch, you'll need to log in with the credentials that you have been sent by email. And then you'll get to the screen and you ask for 8 hours and then advanced reservation HPC Python. And then what we'll do is we won't launch right now. I will give a demonstration and then I'll ask you to launch to make sure that this is working properly, which it isn't. So let's check that the reservation is active. HPC Python. Looks like the reservation's okay. Let's put in, let me log out and log in as one of the course accounts. And then we can check. HPC Python, duration of 8 hours, and we'll click launch. And it says requesting node configuration is not available. So let's try putting in our, also another account, advanced reservation, HPC Python. No. Okay, so what we'll do is we'll move to plan B, and we will, instead of having anything in an advanced reservation, we will simply click launch Jupyter Lab, and that will bring us in. So what you'll see is after a little bit of time, you should get a little blue scrolly line that comes across the screen, and you'll be entered into the Jupyter Lab interface. So ideally, you could ask for, say, 7 or 8 hours, and then you should be able to get in. The only thing is if you ask for 1 hour, then your notebook will stop running. So you need to restart it. Yeah, so Hannes pointed out that I started it with 1 hour. This was a demonstration, so I will now close my notebook and I'll start again with my own login. Okay, so what I'll do is I'll have a quick look on the system, and I'll see that some of you have success. It seems that some of you have successfully got onto the system. Maybe Zhang Donghong is not on there yet. I think everyone else is able to run, if I'm not mistaken. So let me just try to do a bit of debug on why Zhang's is not working. Okay, so what I'll ask you to do is to launch again and leave nothing in the advanced reservation field. So what I'm going to do is I'm going to continue on, and if you're still having trouble connecting after the first, at the first break, we'll make sure that you're up and running here, because this is going to be a bit of a live demo anyway, so it's not so much of a problem. Okay, so first of all, Jupyter Lab interface. What we're going to do is we're going to open up a new notebook, and we're going to grab the course materials from this course. So what we're going to do is type the exclamation mark and then git clone, and then the address of the repo that we've produced for this particular course. And the repo name is eth-cscs/python hpc.git. Okay, and so then you'll type that. Oops, and for me, I've already done it before, so I'll get an error, but hopefully you will get some output from Git saying that you successfully cloned the repo. If you could give a thumbs up or some kind of acknowledgement there. Wonderful, thanks very much. And what you will find is that after you've cloned the repo, you'll get a directory Python HPC, and you can close that notebook there. And basically, you've got a list of directories here with this 3 days of coursework. First of all, I will point you to the 00 materials notebook. So you can double click on that and you can open the notebook. And basically it gives some information about what we've just done, how to log in, and specifically later in the week, if we have updates to any of the course material, what you can do is you can do a git pull. So the exclamation mark git pull, and that will retrieve any updates as required during the course. And then at the end, if you want to download absolutely everything that you've done during these 3 days, you can create a tar file, and then you can right click on it from the file browser and download it to your local laptop. So let's get started into giving a little bit of a demo of Jupyter Lab. Many of you have probably used Jupyter Notebook, but perhaps not so many have used Jupyter Lab because it's pretty new. I think version 1 was about this time last year. It's kind of a completely new interface for Jupyter compared to Notebook. It's much more powerful. You can have multiple different notebooks or other files all inside a workspace, and you can move them around and you can tile them and resize things and do stuff like that. We've been asked to show the link for the GitHub, and I will paste that directly. In fact, I can't. So what I'll do is I'll make a new cell here, and we'll paste it in there, and hopefully you can see that okay. So it's https github.com eth-cscs Python hpc.git. So what does the interface look like? So you've got a main work area, which is this part. And then you've got a left sidebar, and that's collapsible. So we can, if we want some more real estate on our browser, we can click that. And then there's the menu bar along the top. So what you can do in the main area, you can open obviously notebooks, text files, all sorts of other things, images, terminals, consoles, and then you can subdivide them and you can split them and do what you want with them. On the left-hand sidebar, we have, first of all, the file browser. So this is what we're currently on at the moment. And then underneath, we've got the list of running terminals and kernels. So if I click here, you can see that there are currently 3 notebooks that have kernels attached to them. So kernels are basically just the Python process that's running behind the notebook that you can execute code with. And so from here, I can shut down, or I can see what's running and what's not. If I had any terminals open, you'd also see that underneath the terminal sessions. The next tab on the left is the GPU dashboard. And if you can't see that currently, if you just have white space, just right click and refresh the browser, or just do a hard refresh of your browser and it should appear. We will use this tomorrow, so so long as we can get that working before tomorrow, it's absolutely fine. What you can see is, for example, you can see GPU resources, and it will give you a kind of a timeline of what's happening on the GPU. I can move that over here, and so, for example, if I had a notebook and I did something that is using the GPU, so I have a code, I think it's called mmkublaz in my home directory. And I execute that. You can see that basically it's just done a little matrix multiply on the GPU, and you can see some action on the GPU utilization, memory utilization, and you can see the PCI throughput. So how the memory is being moved between the CPU and the GPU over the PCI bus. So you can see also some other things. You can look at also the CPU usage with machine resources and individual information about the GPU memory, and you can move these around as you like. And as I say, we'll make use of that this week. So I'll close them for now. Next on the list is the Dask dashboard. So I mentioned Dask in the intro, but this is a way that you can scale Python code. And here we have a very similar dashboard to the GPU dashboard. So you can see timeline, things moving across. You can see how the memory is being managed. You can set up graphs that show the dependencies of the tasks in your Dask workflow. So we may touch on that during this week. Next in the line is the command palette. So the command palette is very powerful because basically all of the different things you can do in Jupyter Lab can be found through the command palette. So I can just start searching by typing something like restart kernel, and you'll see that automatically you can find how to do things. Okay. So if you're ever in doubt and you don't know how to do something, use this command palette. And then we have a couple more icons, but we probably won't need to use those this week, so we'll continue on. At the top, we've got the menu bar. And again, so this is just standard things like file, edit. You can find all of the keyboard shortcuts and whatnot. And the most important things that you need to probably to be able to do is interrupt the kernel with II, it's double I, restart the kernel with 0, 0. And then you can do things like clearing the outputs, running all cells, and those types of things. On tabs, you can see all the different tabs that are currently available for you. So I have the launcher where you can launch things like a terminal, create a new notebook and whatnot, or you can go to your JupyterLab interface notebook that we currently have open. And then in the help section, it gives you help about not only JupyterLab, but also a whole lot of references. So for example, for Python, for interactive Python, and then references for NumPy, SciPy, and so on. So if I click on NumPy, it will take me to the NumPy website, and you can have immediate access to help without having to leave your JupyterLab session. You could move that to the side and play with your notebook while you have full reference alongside. JupyterLab arranges things in workspaces. So again, this is a little bit different from the classic notebook. Here you can see at the top of your URL, you have lab at the end. If I were to open up another tab with going to the same notebook server, what it will do is it will create a new workspace for me, and that will give that a unique identifier. So the upshot is that you can't have two workspaces. Well, you can have multiple workspaces, and they are uniquely labeled automatically if you create a new one. So I will close that one. You cannot have the same workspace open in two different browsers or in two different browser tabs. So it will always automatically make a new one for you, which is kind of neat. Single document mode versus tabs. So at the moment we have tab view. You can focus on single document mode if you want in the view menu. So you can go to view, single document mode. And so this will remove all of the clutter that you might have on your view. Otherwise you can move back to standard mode where you have all of your tabs along the top or arranged in different windows as you like. Opening files, there's many different ways you can do them. You can either drag them across, or you can double click on them, or you can right click, open, and then you can even choose open with. So if I open with notebook, then it will open it with the notebook application. Otherwise, you can open it with a text editor or some other way that you like. If we look at our file browser, you can see that Jupyter placed us in our home directory. So our home directory on Piz Daint is /users/ and then the username. So for you, it will be something like /users/stud11. It may be that during this course, you need access to the Scratch directory. So it's a Lustre file system, a much larger file system, which is also mounted from the compute nodes. And this is called /scratch/section3000, and then your username. But because we can't go above the /users, so we can't go back up to then go down to Scratch, what we can do is we can create a symbolic link. So you can execute this cell with Shift-Enter, and that will create a link to your Scratch directory. So if we go back to our home, you'll see that then there's a new directory for you, which has appeared here called Scratch. And that will be able to, from there, you'll be able to browse to the Scratch directory. When you create a new file using either the plus and then click notebook, you can rename it by right-clicking on the tab and go click rename notebook. And then type something like rename. And if you want to download something, an individual file to your local laptop, you can right-click on it and click download. But as I mentioned at the beginning, you can also download all of your work at the end of this session by creating a tar file and then just downloading it all at once. For those of you who have not used notebooks before, what are they? Well, they're JSON files, so they're vaguely readable by a human. The JupyterLab reads exactly the same notebook format than the classic notebook did. It's the same notebook server. It's just a different front end. So this is what the first 15 lines of the notebook that we're actually looking at the moment looks like. So you can see that it's JSON formatted. In Jupyter, there are two modes. There are command mode and edit mode. You can see in Jupyter Lab which mode you're in at the bottom of the screen, where it says mode : command mode. In command mode, we can, in command mode, we can move with the cursor keys up and down, and we can move things around and do things sort of command-like. If you press enter, you enter into edit mode, and you can see that the mode has changed down the bottom. You now have a cursor, and also the box has become blue. So you've got a blinking cursor, and now if we move around, we're now in edit mode. Shift enter, regardless of whether you're in edit mode or command mode, will always run the cell. And so here it's a markdown cell, you can see up here. So my new entry has been rendered as markdown. And we can move on to actually running some Python. So code, the default when you make a new cell in Jupyter is code. And so what we do is the standard thing to do is shift enter, and that runs the code, the cell, and advances to the next cell. So you can see that what Jupyter does, which is different from standard Python, is that it actually echoes the result of the last command to the screen. And what it also does is it gives a number to the cell that you've executed. Now, this is important because unlike normal programs that go from top to bottom, in Jupyter, you can do out of order instructions. So I could go and execute a cell up here now, and then that will get a new number which will indicate that it's been executed after this one. So this one will be executed fourth, the next one will be executed the fifth time. Okay, so we like that. If we do two things in the same cell, once you can see only the last operation is actually echoed to the output. So if you really want everything printed, you actually have to put the print statements in like you would normally in standard Python. You can refer to output from a previous cell with the underscore. So here the output from the previous cell is 4. So if we do underscore plus 2, we should get 6, and indeed we do. And likewise, you can indicate a previous cell by using its number. So I mentioned that each cell, when it's executed, gets an identifier. So if we were to do the identifier of 5, which the answer was 3 plus 2, we should get hopefully 5, which we do. And you can use this underscore for convenience if, for example, I import NumPy and then I create a 4x4 random array of numbers, of floats, and then I realize, oh, I forgot to assign that to something. So I want to assign it to A, so I can just say I want to assign the output from the previous command to A. And then if I then create a new cell and type A, you'll see that my array is indeed there. If you want to suppress the output, you can use the semicolon at the end. So if I run the cell, I'll get no output. And you can use the history magic to get an idea of what you've done during this session. So you can see that I started by running that little Kubla's matrix multiplication. Then I created my link to Scratch, and then we looked at the file and we did some things like that. If you put a little question mark at the end, it will give you the doc string for history, and it's the same. This is the same for pretty much any Python object. You can put a question mark at the end to get some information about it. If you want to know what's in your namespace, you can use an IPython magic called who. Magics start with this percentage sign, and so you can see at the moment we've got our matrix A, and we've also imported NumPy as NP. For more information, you can stick an S on the end, and you'll get some more details. The fact that you've got this NumPy array, it's a 4x4 of double precision float, and we've also got imported NumPy as a module, and that tells you where we've imported it from. So likewise, if I insert a new cell and I say b equals 4, and then we run who again, we should see that we'll have an integer of b. And so yeah, this is pretty handy to see exactly what's in your namespace pretty quickly. Now we have some Jupyter Lab specific features. You can drag and drop cells. So I can just pick up this cell and I can move it like that and move it around. So something which was not so easy to do with classic notebook, but it's been enabled with this more advanced interface, Jupyter Lab. You can have multiple views of the same notebook. So if I right click on my tab, I can click new view for notebook. And here I have exactly the same notebook. It's literally the same, so it's has the same namespace, the same kernel it's attached to, but I can move through them independently. So imagine I want to look at two different parts of my notebook. I've got a really long notebook and I want to see something here, or I want to see something here. So you can have two versions of it running at the same time. You can drag cells between them. So you could either drag cells, if you have the same notebook open twice, a drag across will copy and paste. And if you have two completely different notebooks, it will paste, which is probably more sensible. If you have some boilerplate that you need to move across, you can just pick it up and drag it across to another notebook. You can collapse and expand the cells. So you see this little blue line on the left-hand side. I can click that and it has compressed the cell. So if we want to have plenty of space, we can compress these and then you can expand them again by clicking again. You can also enable scrolling for long outputs. We can see that, for example, when we did our history, we have a scrollable cell. And that did it automatically for the, here we can right click and disable scrolling, and then you can see the whole thing. We can right click, enable scrolling, and you can do that for any kind of notebook that produces, sensible for things that produce a lot of output. You can create brand new views of output. So here I'm going to open up the Lorenz notebook. This is kind of a famous one, which is always shown in demonstrations of Jupyter Lab, solving the Lorentz system of differential equations. What we'll do is we'll run a few of these cells and we will get to a point where we have a kind of interactive dashboard. So here we can change some of the parameters by using a slider. What we might want to do is create a new view just for this cell output. And so what we can do is we can right click, and then it should be enable new view. Create new view for output here. And here you can see that what it's done is it's created kind of like a very lightweight dashboard. And so you can move your original notebook back to some of the more interesting part of what you're doing here. And in the meantime, you've got a completely separate mini dashboard, which is fully functioning just like it was in the original one. So these new views are pretty handy in these notebooks. Improved tab completion. So if we import NumPy, if you want to create a random array and you've kind of forgotten the syntax, you can type the tab button and keep pushing tab until it will find, there we are, tab complete.random. And then if I keep clicking tab, then you can see what's available there. And I remember I want rand, so I can just keep tab completing, and then I push shift enter and it will give me the dot string, and so I can remember that this is the arguments that are required for that. Terminals. So we have a fully functioning terminal in Jupyter Lab. You can get that in a variety of ways. You can either do file new terminal, or we can use our launcher. What we can do is fire up a terminal. And where has this landed us? It's landed us on the compute node that we have been allocated. So my host name is NID07151. You will have your own individual compute node, and you can do standard things that you can do with a terminal. Like you can run top, see what's running. You can look at the CPU type that's on this machine, and you can see that there's 24 cores. It's an Intel Xeon CPU, or E5 V3, which is a Haswell-based Intel CPU, and running at 2.6 gigahertz. One thing to note, that if you close this terminal with the X, the terminal doesn't actually stop running. And you can see that because if you go back over to the running terminals, you can see that our terminal is still running. And so we can shut them down there. Or if we create a new one, we can type exit, and that will close the terminal. And so you can see no terminal running. So that's just something to bear in mind. You should be able to copy and paste stuff from the terminal, depending on whether you're on Windows or Mac. The keys, or Linux, the keys will be different, but typically you can usually find a way you can copy and paste. As I mentioned, command palette is very powerful. So you can click here for command palette and you can search for anything you like. So if you forget how to do something, use command palette. Is our home, so there's a question from Francesco, which is our home accessed in the compute node? Meaning, can we move around our files? So you should be able to see the files that are in your home directory on Piz Daint. So at the moment, that will pretty much be only what you have checked out from Git. So it will be, for example, this HPC Python HPC rather directory. So indeed, so the compute node does mount the home directory. Yes. The server itself is actually running on the compute node. So as the server can see your files in the file browser, likewise, the terminal can also see your files. Thank you for the question. Creating new views. Now, this is where JupyterLab becomes pretty cool and powerful. So imagine you've got a text file, for example, a markdown file, and you're doing some documentation. We'll open the markdown file with an editor, and so it's a pretty basic little thing. What we can do is we can create an alternative view for it by opening with also the markdown preview. Now let's just move them side by side. I'll make a little bit more space on the screen. You can see that this is the markdown in your text editor, and this is its rendered live. So what we can do is you can actually edit directly. And you'll see that it's a live preview of the rendered markdown. So it's kind of cool. And what is cooler is that you can see that I've got a code section here, which is delineated with 3 backticks, enclosed with 3 backticks. And so imagine that you're creating some documentation, and you have some code snippet in there, and you want to check that the code snippet actually works. What we can do is we can right click and we can add a new console for the editor. So you can choose which kernel you want. I want a Python 3 kernel, so I click select. And here you can see now that this we have a Python process which is connected to this markdown file. Right, so what can we do then? So what we can do is we can select a line of text, And we can shift enter like you do in a notebook, and you can see immediately that it's actually run that code segment in the console. If I don't select any text, I just click inside this backticked code segment and I press shift enter, it will run the entire cell. So the idea here is that maybe you'll write some documentation and you want to test that your example documentation actually works. Maybe it renders some image. You could run it in the console, create the image, and then the image would directly be entered into your documentation. So you'll know that that your documentation is self-consistent and it's going to work all the time. So these sorts of things are really beautiful in Jupyter Lab. I'll close this up and we'll go back to our tutorial. So IPython provides these magic commands. We've seen a couple of them already. They start with percentage signs for line magics and 2 percentage signs for cell magics. Line magics, everything's on one line, the arguments to this magic, and cell magics, it uses the entire cell as arguments to the command. To see what we've got available, you can shift enter on the ls magic command. So the ls magic itself tells you what magics are available, and then you can, it's produced a dictionary, so you can then expand that and see all of the different magics that are available. Some of the ones that we will use this week are the most powerful. For example, time it, you will see that somewhere in there, but you can also do things like catting files, ls, whatnot. What I'll do is I'll right click and I'll enable scrolling, whoops, and then you can have a somewhat better view. So there's things like time it, and that's what we're going to use right now. So we have 3 different magics that we'll use to time snippets of code. Obviously this week's all about performance, so we're going to be needing to determine performance. What I do here is I just import NumPy, and from numpy.random import a random integer, and then I return random integers, 1 million of them, which is kind of simulating 1 million rolls of a dice. So if I shift enter that, what I'm going to use is the time first of all. So this is just percentage time, and we will throw 1 million dice, and then we'll calculate the mean. So we're rolling from 1 to 6, we don't include 7, and we'll run it once, and what we get is the wall time is 10 milliseconds to throw the 1 million dice, and we have about 1 millisecond to calculate the mean. And it tells us the mean is 3.5, which is, I hope, what we would expect when we're rolling dice. So what's happened here is this has run 1 instance of timing this line and run 1 instance of timing this line. And we got 10.7 milliseconds and 9.47 microseconds, not 942 microseconds. If we run it again, you'll see that the numbers are quite different. So this time we got 11 milliseconds. Last time we had 10 milliseconds, so that's like 10% difference. And if you're optimizing code, 10% for doing nothing is a bit of a concern, because you won't know whether what you've done to your code has actually improved it or it's just random noise. So for that reason, we have this time it. And what this does is it runs this many times. And the number of times that it runs it, it works out itself. And the idea is that it tries for the total time to take a couple of seconds or so, between 2 and 3 seconds. So if I run this, we can see what happens. The first line should take about 3 seconds. The next line should take about another 3 seconds. And we can see that indeed that has done that. And what it did was, for the first line, it ran 100 times. And then it did 7 runs of those 100 times. So it did 100 loops, and then it did 7 repeats. It gave us the mean and the standard deviation. And so we saw that it took 7 milliseconds with a standard deviation of 9 microseconds. So we have a much better idea of the reality. For the second part, when it did the mean, remember this took a much shorter amount of time. And so it was smart enough to do that 1,000 times. And it found that the timing was 798 microseconds. If we run it again, we should see that we should get very similar results to what we did last time. So we know that the timing is real and it's not just some random noise. So yeah, last time we had 7.32, I think, very similar anyway. And so you can see that it's working well. You can time the entire cell using the cell magic. So we do time it with the cell magic. And that will do the whole step all in one go. So we should expect it will take probably 8.1 milliseconds. It's much more accurate way of timing. If we want to write files, we can use this magic called write file. So here we're just writing a Python file. We put some code in there. We just shift enter and that creates the file. You'll see in our file browser will appear a new file called Python HPC snippet, and it has appeared indeed right here. You can look at that file using PyCat, which is kind of like a cat in Linux, but it also gives you some syntax highlighting from Python. If you want to load the file, you can use the load magic. The load magic is pretty cool because the first time that you run it, it loads the file into the cell, and it also comments the load magic. So then you can run it again a second time, and it will actually execute the cell. Another thing you can do is run files directly from your notebook externally with the run magic. So here we run that, and so I think that the Python HPC snippet, all it did was printed writing a file with write file. So this has executed that. How to get help. So over these 3 days and 3 nights, you can get help with the question mark operator. So global help simply from question mark itself. And then any object, you can use question mark after it. So if we import NumPy, for example, then we can do np question mark, and it gives us the doc string for NumPy. All right, and some examples and everything like that. Shift tab again will also give you a doc string. So if I go shift tab on this one, you can then scroll through the help. So you can see that the help's pretty powerful. We also have wildcards, and you can do that with the star, the asterisk. Here I assign a string hello to mint, and then I want to know everything which is in my namespace, which has int in there somewhere. So we have int mint print, for example. There's a quick ref as well that's available from this magic again. It's quick ref mag, and you can then find all of the IPython specific, so the IPython reference card. For many things in the notebook, it's great to use keyboard shortcuts. So I list them all here. You can play with them at your leisure. But in worst case scenario, if you need to use the mouse, you can generally find everything by going to the command palette and then just starting to type what you want to do. Some important things are DD to delete the current cell, kind of like how you delete a line in VI, but not quite the same because it doesn't save it to the buffer, so you can't then paste it. It really just deletes it. Z to undo the cell deletion. If you want to change a cell to markdown, so there's 2 different types of cell, markdown and code. M for markdown, Y for code. And then, yeah, restarting or interrupting the kernel II, restarting the kernel 00. That's pretty much all there is to it. So the next thing that we're going to do is to pick up the 02 install kernel notebook. And what we're going to do here is we're going to create a custom kernel that is going to be used for the exercises this week. So this is very important that you work through this notebook. And at the moment, everyone has a Python 3 sort of default kernel that comes with IPython. What we're going to do is we're going to install our own kernel, which is built on a Conda environment that Rafael has prepared for us. And that has some additional things in it, like Numba and CuPy and those types of things we'll use this week. So it's really important that we get this installed. What is a kernel? This is basically what's running, this is the Python processor, which is running our code cells. And the Jupyter lab looks for kernels that sit in your users std xs .local share Jupyter kernels. This is where it's looking for kernels. So we need to install our kernel in that path. The important files are kernel.json, which has a set of arguments to tell it how to launch the kernel, a display name, so what the kernel will look like in this Jupyter lab. So here it's just displayed as Python 3, and the language of the kernel, which will be Python 3, both in our current case and the one that we will install. So first of all, what we need to do is create a directory for our new kernel. We're going to install it in the directory miniconda-python HPC. So please execute that cell. And then what we're going to do is we're going to write our kernel.json file, and we're going to use the bash magic to write the file. So we're going to, until the end of this file, we will write this lot to this file. Again, we have a display name, so it's going to look like miniconda python HPC. And then the language is Python, and then we will tell it what arguments to run. And what we're going to tell it to run is a file called launcher. And basically launcher will activate our Conda environment, and then it will start the IPyKernel. So we run that cell. And then, of course, we need to create that launcher file as well. This is kind of the helper file. As I say, what it does is it clears our Python path, and then it source activates our Conda environment, and then it launches with Python the IPyKernel launcher. So we also run that file. And then the last step, or last but one step, is to make that launcher executable. So here we do a chmod plus X on that file. And we press enter. And then as an additional step, what we want to do is whenever we open a terminal in Jupyter, we also want to activate our Conda environment that we've just created. So what we should also do is to add a line to our .bashrc. And we can do that by echoing the activate, the source activate to bashrc. And then we've got a couple of exercises that should hopefully show you that you're able to use your new kernel. So before we switch to the new kernel, so you should have Python 3 up here in the top right-hand corner, or also bottom left-hand corner. If we execute this cell with Shift Enter, we see that NumPy is version 1.15.1. This is coming from our Python 3, and the path to this is through the method _file_, and you can see that it's in OPT Python, which is kind of the default Cray Python environment. Now, what we will attempt to do, oh, there's a typo here. So now we will shift to our miniconda Python HPC. So what we do is we click switch kernel at the top, and hopefully miniconda Python HPC kernel will be available for you there. Let me just correct this typo. And hopefully you've been able to successfully change to your Miniconda Python HPC. Maybe throw us a wave or a thumbs up if you've been able to do that. For those of you who can't, don't worry, because in 5 minutes or so we'll have a break and we'll make sure that we can get everyone sorted out. So now we can kind of verify that we're now in a different environment. Thanks to everyone who's raised their hand. It looks like most people have been successful with that. So now we can see that we've got the Miniconda Python HPC kernel, and we're going to do Shift Enter on that. And now instead of Python 1.15, we've got a newer version of NumPy, newer version of NumPy 1.17.3, and you can see that it's provided by the package which is sitting in this kernel that Rafael has built for us specifically for the course. And then you can do things like look at what linear algebra library is NumPy is linked against by using the np.show config. And you can see that it's linked against MKL, which is Intel's fast math library. Math kernel library. And then you can also confirm that Numba is now available. So on our old kernel, if I switch back to the Python 3 kernel, and I try to execute some Numba, it will say it cannot be found because Numba is not provided in this default kernel. But if I switch to Miniconda, the one that we've just created, and I Shift Enter, you can see that Numba provides some information about the architecture that we've got in our system. So you can answer questions like how many CPU sockets we have, are there any GPUs? If so, what is the device type and architecture? And to get that kind of information, you can see that there's a Haswell CPU with 24 virtual cores, and this is how they're addressed. And then if you scroll down a little bit, you should find some information about a CUDA device. It finds that there is device ID 0. There's one GPU. It's a Tesla P100, which is connected through PCI, 16 gigabytes of memory, and compute capability 6 and whatnot. So I think according to the timeline, we have reached 10:15, which is time for a break, and we've completed everything now that we need to be able to continue with doing some real work after the break. So what we'll do is we'll have 15 minutes now, and we'll come back at 10:30. And those of you who have not been able to either launch the notebook or not been able to install the kernel, then please, we'll be available for help during this period. Okay, we won't get going quite yet, but I'll answer some questions that are appearing in the chat window. So first of all, Jordan has asked, what are the differences between Jupyter Notebook and Jupyter Lab? And for a computational scientist, which do you prefer? So of course, as you've seen with Jupyter Lab, you can do a lot more stuff because you have a much richer, it's kind of a more IDE-like environment. You can open all sorts of different files. You can interact between the different types of files, as you've seen. Whereas Notebook is a little bit more primitive in what you can do. So Notebook uses quite old web technologies, and for that reason, it's not easy to do things like moving cells around by dragging and dropping. And they really wanted something that was a little bit more modern. So they created Jupyter Lab. The question of which one to use, well, Jupyter Notebook will actually be retired. So Jupyter Lab will at some point become the only notebook that's available, unless something else, if they develop a newer thing, but they certainly intend to retire Jupyter Notebook. So you should switch over. However, there have been some recent surveys on usage, and some people prefer the notebook, Jupyter Notebook server, because it's a little bit simpler. And I guess they're more familiar with it. So it's a little easier if you're not used to Jupyter Lab. Maybe there's so much going on. It's like any change, you know, a new interface comes along for anything, and for the first few months, people don't like it. But yeah, it will become the default interface, so you may as well start using it. It's much more extensible. So in Jupyter Notebook, you could have extensions, but you couldn't have such an interaction between different things. So I would say personally, I like Jupyter Lab because I can use things like the Dask Lab extension, so I can create a Dask cluster automatically by clicking some buttons, and I can drag things across. I can look at these dashboards without having to open a brand new browser window. So with Dask, for example, if you're using Notebook, you can open the dashboard, but it becomes another browser tab. So then you have to switch between the tabs. In Jupyter Lab, you can arrange different windows as you like your environment to be. So I would say it's a nicer environment. It's more like closer to something you would expect from commercial products like MATLAB that maybe computational scientists are moving towards these days. We had a question from Giordano, who's still having trouble starting the notebook. So we have our system engineers that are checking the reservation at the moment. So hopefully it will work soon. I think, what was this? It looks like maybe it's running now. So your user account, I think it's working now. Yeah, okay, so just managed to connect and download the repo. So apologies for that issue. The important thing to do is, so download the repo and then go into the Jupyter Lab directory. So HPC Python HPC, and then Jupyter Lab, and then go to the 02, create the kernel, and run all the cells in that one. You can go and play with the 01 Jupyter Lab later, but the important one to do is to install the kernel. So just run all cells, or just keep pressing Shift Enter. Okay, so just before Rafael gets started with his section, we have one more question about Jupyter Notebooks, and that's from Enda Carol, or Carol Enda. And the question is it possible to set up Jupyter Notebooks in a virtual environment? This is important because a lot of people like me don't have root access on a system, and so you need to use virtual environments for specific versions of specific packages. And it's absolutely the case, yes. And it is more or less what we've just done. So all you need to do is, it doesn't matter whether you're using Python venv or you're using Conda. You can create a virtual environment yourself, and you can install Jupyter Lab. So all you need to do is pip install or -- upgrade Jupyter Lab -- user, and that should install everything that you need in your user space. Now, if you want to use that through a service provided by someone else, like a Jupyter Hub that we provide at CSCS, or some other service that Binder or the cloud is providing, then it's not so trivial. But you can absolutely, on your local machine or on a cluster, you can install Jupyter Lab yourself. If you may need to then create some tunnels back to your local machine in order to be able to get the Jupyter server to render in your browser, but it can usually be done. So yes, absolutely, you in fact should really use virtual environments for Jupyter. Okay, so I see on my terminal that I believe everyone has a notebook running now. So I will hand over to my colleague Rafael, and we'll start the next section. So thanks, everyone.
Thank you, Tim. Good morning, everyone. Let's see a second how to share. Can you see my screen?
Yes.
Okay, thank you. I can't. There is a black. I'm sorry. I'm sorry. I have a black window in the front of my screen that I don't know how to take, and I guess it's from Zoom. Yeah. Okay. I still cannot see, but fine. Good morning again. I'm Rafael. Today we are going to, from now to the end of the day, we are going to go by a set of examples. And the idea is more or less to introduce you to some of the most popular packages to do high performance computing with Python. And then we're trying to get you started. We're going to see just basic things. And then the idea is that you later after the course, you know where to go. And if you want to see any of the things in more depth, you can, you already have some steps in there. Before going to examples, we're going to see some points of Python that they are going to be important for the course and in general for this kind of work, which are the reference counting, garbage collection, and the GIL in Python. Tim already mentioned that Python is interpreted, and we all know that Python, we can use it for scripting and doing very quick stuff, and we all like it. But why Python is so popular, and there are so many libraries for HPC. But the thing is, but there are many reasons. But one of the most important is that most of the operations can be overloaded. That means that you can write a new code and adapt all the sum and the properties of objects of Python to your interest and the way your code want to work. If you have seen, for instance, TensorFlow, how it used to work last year, when you do these sums, it was Python code, but there was no sum happening. What you were doing in the background was to creating computational graphs that later were going to be executed. This is what means overloading the operations. And the other point is that it's fairly easy to make bindings to other to more powerful programming languages like C and Fortran. And through this, you can have access to sophisticated stuff like getting the best of the CPU features and do complicated memory management and doing using accelerators and so on. And actually, in Python, when we run most of the things, or if we use NumPy, that we use it almost every time, the Python runtime looks like this. You have a Python thread that in some point may ask a function that is compiled in C. That many of the NumPy functions, for instance, are compiled in C. Or maybe you have CUDA code, something external. Then this function will do something, and will return, and your Python thread will continue. Then you can run another one, and so on. And then you can even create threads or processes that can run different things in Python. And it's always like this. Most of the cases it's hidden. When you run it, somebody else, the developer of the packages, they hid that from you, or the C code or all the Fortran is wrapped in Python, so you never see the C. But in the background, Python is using this kind of things. Now let's start with this part. Let's have a look to the reference counting and garbage collection. This is a very, very, very high-level overview of the memory management in Python. In reality, it's very complicated. There are many cases, but this is just to have a good idea, and will help us during the course. Okay, let's consider this example. Let's say this is a script that starts, you create a NumPy array, a random array, and you assign it to A. So when you're doing that, in the background, by the way, this notebook is, this presentation, if you want to watch at the same time instead of Zoom, it is on intro, on the repository on intro. I don't remember the name, but it's on the folder intro. Okay, sorry for interruption. You create a NumPy array, and you assign it to variable A. And the background, what you are creating is a location in memory. That is a continuous block of memory that some binary inside. And when you create something, Python will update the reference. The reference is in the number of variables that point to the memory. So the reference is not to the variables, to the memory. Now, if you do another operation, I said your script continue, you do the transpose of A and you assign it to B. This operation we are going to learn later, that doesn't create new memory. It just does some changes and reuses the same block of memory. Since the same block of memory is used by two arrays, by two variables, the reference is going to increase. Initially we have 1, and now it goes to 2. So this is very important, the reference counting. So let's say our script continues. We create two other arrays. They're going to be allocated next to them, next to what we already did. And the reference is going to be 1 and 1. And now let's say we delete C, the variable C. What is going to happen is that this operation here, del C, is going to set the reference count this memory here that C was pointing to 0. It means that this variable, sorry, this memory here, this location of memory, doesn't have any variable pointing to it. There is no reference. And now there is another thing that is called the garbage collection, that are cycles that occur in Python. That is a mechanism that is checking the memory. And when it finds that a memory location has a reference equals 0, then the garbage collector, it will mark it as free. Now this memory here appears as free to Python, and if you do something else, you create a new variable, it may put it in it can reuse this memory. One important thing is that this memory doesn't appear free to the operating system. This memory is Python has it. Python can reuse it, but nobody else can use it outside Python. Okay. Now let's say that our script continues. Sorry. Before that, I want to clarify that this operation here, so we did there. It was clear that put 0 to the set 0 to the reference here. And the garbage collector sees as mark is as free. But another way to free the memory or to set the reference to 0 is if we see C equal, if you do C equal 1. So initially C was pointing here, but now when we say C equal 1, C is going to be pointing somewhere else. So this place here again, this memory, is still not referenced. So an operation like this will also set this location in memory as a reference 0. Okay, and the garbage collector will mark it as well as free. Now, if in our script later we create an array, we say that with this n or something bigger than the memory that we located before, this n is larger than m, this memory doesn't fit here, and there's no such a thing as putting part of the memory here and part of the memory later. The memory of NumPy arrays is allocated as a continuous block. If you do this, this block here is going to be still unused. It will be only used if you create something later that fits in that memory. If that happens, Python can go and allocate this memory and reuse this memory, and then set the reference to 1 again, or depends whatever you're doing. Okay. Now, if this is more or less clear, I hope so. I cannot see the thumbs up, but I hope it's clear. If now that it gets a bit complicated, if we run this thing that we did here into or more threads. So if we do threads, the reference counting, if the reference counting into different threads is different, that can cause conflicts, because and it's something inherent of this way of doing memory management through reference counting and garbage collection. If you have two threads, it can happen that one is changing, both are accessing this variable, the reference, at the same time, and then they can corrupt the reference. And then the garbage collector may find that, for instance, something was set to 0, whilst it was not supposed to be 0, and then it will be free. And then the rest of the program is expecting to access its memory, but it already disappeared. Or it can be that something, it was supposed to be free, but the two threads corrupted the reference counting, and now the thing wasn't free, and it's creating it's leaking memory, and your program is going to use more memory and it can crash. Or it can happen that you just get weird results that you don't know what is happening. To get around this and to solve this problem, Python uses something that's called the GIL, which means Global Interpreted Lock. The GIL, for sure you have heard about it. I remember for a long time not knowing what was the GIL. I heard releasing the GIL, acquiring the GIL, but for my day-to-day job, I never cared what was the GIL, because this is something that happens automatically. But now, if we are going to write or do HPC code with Python, we need to understand what is this. And later in the other exercises, tutorials, we're going to see examples, and I think it's going to be more clear. A GIL is a lock, and a lock in computer science are mechanisms to regulate the limit to common access, to common resources during situations where there are multiple threads. And common resources can be memory, for instance, an allocation, like the reference. An allocation, a memory address protected by a lock will mean that only one lock can use it at the same time. To understand more or less how a lock works, you can find in the internet a lot of analogies, but the thing goes like this. There is a kind of game that the kids and the teachers, they do in kindergarten, which is there is a bunch of kids, and all of the kids, they have to make a story, but only one kid is allowed to talk. And to allow a single kid to talk, what the teacher does is it gives the kids kind of a puppet, a toy, and the kid that has the toy, that acquired the toy, is the only one that can talk. And if you have the toy, the rest of the kids are blocked. They are not they are not allowed to talk. If for a kid to talk, he has to wait for the kid that has the toy, for another kid to talk. He has to wait for the kid that has the toy to release it, to give it to another, to pass it, and then this one can talk. And like this, all of them can talk, but only one by one. The same thing happens with the lock. The locks, in general, in computer science, not only the GIL, they have two methods: acquire and release. And now I'm going to show you an example in Python that how this works. Here we have a notebook that we are going to use the threading module of Python to create threads, and we have these two functions. So if we have a look here, they are very simple. There is a for loop and a for loop over another for loop over words, and then at the end there is a print that is going to print that word, right? And I just put here the C is a color. This one will print it in red, and this one is going to print it in green because we want to see the two answers. So here we are going to create two threads, 1 and 2. If you don't understand very well the syntax because you haven't used it, don't care too much. The idea is that this line is going to create a thread that's going to run function 1, and this one is going to run a thread that's going to run function 2. We are going to start it, and then we're going to join it to the main thread. That's it. This is something very simple. So here we are using the print function, and if we run it, if we run it, we're going to see that this for loop and this for loop, the printing, they are interfering with each other. And our thing is always different. You get hello red, which is the first function, and then a bit of green. If we run it many times, this one was fine, but every time it's going to be different. This one, we're running without, it's two thread running without lock. Of course, here we are only simulating that thing. If you see that there is no, the hello is not, there is no word broken. And there is no word broken because the GIL is running, and everything is protected by the lock. The print function, we cannot make it run at the same time, but we can simulate those threads interfering with each other through the for loop. Okay, so everything is different every time. And now we're going to do an example with lock. Here we have the same thing, and the threading function gives you a lock, and the lock has acquired and release. We have the same function exactly, and we are going to wrap this for loop that were interfering with each other. We're going to wrap it by lock acquire and lock release, which this means the first thread that starts will run this one, And same as the kids, when you run log acquire, it's like when you acquire the toy, in this case you acquire the log, you're going to block the other thread, and only this thread can run. So this thread can run, and the other one has to wait. When this one finishes whatever he's doing, the for loop, it will release, and only the next one can acquire the log. It can happen that this one acquires it faster, but you get the idea. Now, if we run this, I did it wrong. Now, every time we run, everything is going to be fine, because the log, the threads are not running at the same time. They are running sequentially, one after the other, because we put a log. Okay, so remember, this is not the GIL. We're just simulating how the GIL works. And in Python, this way, similar to this way we wrote our code with docs, Python itself is written like this. When you have a script that you have, this is not exactly like that, but more or less just to get an idea. Every line of code, the interpreter, the interpreter will translate it to machine code and some instructions. And when they are run, these instructions, when they are run, they are going to be wrapped by this. So anything that you run in Python, although you don't see it, will have at the beginning log acquire and log release. And then if you try to do it multi-threaded, Python itself won't allow you to run both at the same time. For instance, one of these instructions can be the print function. Here, although we got everything a bit messed, we don't see any hello or any from broken apart, because the print function, this instruction, is protected by the log. Okay, but now I think this is a bit hard to understand the first time, but we're going to do through the day many exercises, and so many of them you can see the effect of the GIL, and we have to reason. Okay, this is because of the GIL, or this one is because the GIL is released, and this kind of stuff. If you want to run Python code truly multi-threaded, you have to start your code with log release. But it's not this log release. It's something that you have to write in C using the Python C API. It's something like it's at machine, not a machine, at code level of Python itself. With your code from the Python interpreter, you cannot do it. Okay. In this, just a very small comment, there are two ways the GIL is implemented in Python. They are separated in CPU bound and IO bound. IO bound can be like when you're waiting for a system calls. For instance, if you are going to write a file that is not CPU intensive and it's also slow, in general, in Python, these things are implemented like they release the log first and then they acquire it back. Which means, remember that I told you, everything that you run in Python will acquire the log first. Now, these kind of functions will release it, and they will run. And this, which means that these functions can be run truly multi-threaded with two concurrent threads. Okay. The other one is CPU bound. There are things that are calculations or accessing memory that are more it can be affected by multi-threading. All these things are protected by log. All of these of those acquire log and release log later. And this example of this can be you're doing a transformation on a list or something that is CPU intensive. You do some kind of calculation, not in C, because in C it's not Python code. It's you can change where you're more free of doing other things. But if it is Python, they will be protected by log. But again, we are going to see later examples of this. For instance, in NumPy, this is a C code. If you look in the code, you will find things like this, like a NumPy loop begin threads or begin threads and NumPy end threads, or all these things are releasing and acquiring the GIL In many cases, NumPy, many functions are multi-threaded, so they release the guild. And also functions that are not multi-threaded, they release the guild, so you are you have the possibility to run them truly multi-threaded. Okay, and this one again, we're going to do exercises with it. Now, if you have some questions, I don't know how to see the chat.
No questions at the moment, Rafael.
Okay, good. Anyway, if thank you, Tim. If you have questions later about this, tomorrow we have a Q&A session, and we can talk about this, or just type it and we can in another session, and I will save it for later, and I will discuss in another moment. Okay. And now, before passing to the next session, I'm going to talk a bit about the Python distributions that we use in Daint, how we run Python in Daint. So for the ones that are new in the machine, you have more or less an idea how we do it. So in Python, we have firstly in Piz Daint, we have a create Python module, which is a Python distribution that is provided by Cray. You can load it like this: module load, create Python, and the version. And the main difference, the main particularity of this create Python is that the backend for NumPy is by Cray libsci, which is a math library of NumPy. It uses the libraries installed by system in the system by Cray, sorry, and in general are optimized for Cray. We also provide something called Py extensions that you can load, and then you get their Python, NumPy, pandas, and matplotlib, this kind of basic programs that we use day to day. We have things built on that, like TensorFlow, for instance. And you can install your own packages if you want in a virtual environment or in your user with pip. Then we also can have conda in Piz Daint. It's not provided by default. You have to install it yourself, but it's very simple. You can choose Anaconda or Miniconda. In general, we recommend Miniconda because Anaconda install a lot of packages that you may not need. And the main difference with Cray is that it uses, for the backend of NumPy, MKL. So if you run this, you will see MKL here. Okay. And Anaconda has a particularity that is that when you install it, it brings almost all the libraries that, even not Python libraries, just like system libraries, which at the end you only need, I think, is the drivers. All the rest of the stuff they bring it, and because of this, you cannot mix it with Cray modules. You have to try to have Anaconda as an isolated environment, because otherwise you can get conflicts. Okay, you can install things with conda install. There are different channels you can find in Google if you haven't used conda yet, or you also can install pip. Okay, and finally, I just want to point out that pip, the packages installed by pip, they come from PyPy. This is a repository of Python packages. It means Python packages index. What you get in general are binaries that are already pre-built somewhere else. So they are not going to use they are going to be as performant as binaries built on Piz Daint, because they are built for general architectures. If in general most of the cases that doesn't matter, but there are packages that are very sensitive to such things, and for those cases it's better if you build it yourself on Daint. Okay, an example is again TensorFlow, that the building process takes in account the features and of the CPU, and it builds specifically for the one CPU. And if you get it from PyPy with pip, you may get something generic that is it's not going to be as performant as one built it in. Okay. So here we stop this introduction part, and we can move on to our next example. Sorry, to our set of examples. Here, managed to close the window that I couldn't see. Now we're going to start with NumPy, but through the day we're going to work in a single problem almost, which is implementing distant matrices. And we're going to start with NumPy and SciPy. We're going to do implementation there. Then we're going to try to get it better using Numba, and we're going to do some basics of Numba, which is, Tim already mentioned, is a library that allows you to translate Python code in machine code optimized. Today is very basic, but tomorrow you will learn a lot more with Theo, more in depth, more advanced stuff. Then we're going to do a parallelized version with Dask that will run with through a computational graph. And tomorrow we're going to do the same in Fortran and in C, and we're going to create bindings to those functions so we can run it from Python. Okay. So let's start. So what is NumPy? NumPy, for sure, we all know it is a standard library that we all use if we want to do a numerical calculation in Python. So NumPy adds to Python support for multidimensional arrays, and also a lot of functions to do computations with these arrays. The main object of NumPy is called the NumPy ND array, which is an n-dimensional array object. NumPy has very sophisticated functions written in C, most of them. Then you can find the linear algebra, Fourier transform, random number capabilities. And it brings something called F2Py that allows you to write bindings of Fortran code to Python. That one we will see tomorrow. And it also is compatible with C, that we also will see tomorrow. Together with NumPy, there is SciPy, which is sort of an extension of NumPy. It builds on the NumPy array, and it includes a lot more of operations. Again, very sophisticated everything, written in C. And then you get numerical integration, statistic, linear algebra, optimization. It's like a toolbox. Most of the things that you want to do, you can find it there. Okay, so we are going to start seeing some internals of the NumPy array before the examples. So this is for sure you know what is this. We are creating a NumPy array from a list, and then we get a 3x3 matrix, and here we specify type int8, which means every single one of these numbers is going to take 8 bytes. Okay, how this looks in memory? Well, in memory there is a block of memory. Everything of these things is 1 byte. You have the 0, then you have the 1, the 2, until the 8. I put this dots here because since it is 1 byte, who's going to get too large the picture? But you get more or less idea. So this block of memory has the data, has the numbers, but doesn't say what is the shape or what is the single element, if it is from here to here or from here to here. For that, the NumPy array has something else that is called metadata. I'm sorry, here I just divided the numbers, I forgot about it. That is called metadata. And this metadata tells Python how to interpret this block of memory. So here we have the shape, it's 3x3. We have the type. Now we know that one single number is this. And we have the strides that we're going to learn later how to do it, how to understand what it does. And so the thing is called metadata, as already said, and the block of memory is called in NumPy language data buffer. The data buffer is stored in C order, which means row major. This means that this one is going to be, the rows are going to be stored first, and then the columns. If we go back here, we have a row is 0, 1, 2. And here we have 0, 1, 2, and then the next row like this. Okay, column major should be that you start 0, the next one is 3, and then the next one is 6. Okay. So let's see an example of how things work. Again, this is again a block of memory, but I didn't put it in binary, put it in decimal numbers, so it's easy for us to read. Each of them are 8 bytes. It's int 8 bytes. Again, we don't know the shape. We don't know anything about this block of memory. We need the metadata. Our metadata here is saying that this is a 4x4 element array with this order. Okay. And then here I put the most important parts of the metadata. We have the type, which is int 8. It will tell us, or it will tell Python what is a single element. It's 8 bytes. It's not this whole thing. It's just one single element, 8 bytes. We have the shape. Tell us this thing is organized in 4x4, and there is a stride. So the stride is a bit harder to understand in comparison with the shape. But the strides will allow us to do something very cool, which is operations that do not require change of data. Change of data buffer, only change of metadata. One of the things is transpose. If we transpose this, the only change that is on the array is that the stride changed from 1 to 4. We didn't have to change from 4.1 to 1.4. We didn't have to change the memory, which is expensive. We only changed a couple of numbers on the metadata. And this, then what is a stride? Well, the stride tells us how to find, given the indexes of the array. For instance, this number here is 3,1, the 9. How, given 3,1, Python is going to find that on the memory buffer. That's why we could do the transpose only by changing the strides. Okay. How it works is the first element of the stride will tell us how to move in from one row to the other one. This one means that that 8 bytes, no, 1 int 8 bytes. You need to run. You need to move to go from 0 to 1 in this direction. Okay. So if you go in this direction, you're moving here 8 bytes from this one to this one. To move in this direction, we need to move 4. So if you want to go in this direction, to get this element here, Python knows, looks here, okay, I have to move 0, 1, 2, 3, 4. We have to go here. Okay. Same in the original representation, in the original position of the array. Remember that we transpose it. If in this original version, if we want to move here, now we have a 4. So now we don't move only to 1, we use 4. We move to the next row. And if we want to move in this direction, we move only one set of int 8, no? 8 bytes. We move here. And the position, the final formula to find the position here with respect to the indexes, which is like what I said before. This one is 2, 1. This one should be 2, 2. When you give the NumPy normal axes that indexes that we use, say human accessible, user accessible, and through this equation, stride 0 times first index, stride 1 times second index. It will give you which position here it has to give you back to you when you initialize this. Now let's go to a notebook and play with this a bit. Here we're going to open, let's go to the notebooks and open NumPy 01 and NumPy array internals. And here you have the order of the exercise. The idea is we're going to understand a bit strides to play in by playing with them, and then we're going to see how to, if we can guess if an operation is only metadata modification, or we are changing the data buffer. Okay, we are copying data buffer. So let's go to the notebook.
Can I, Rafael, it's Tim here. Can I just interrupt for a second?
Sure.
So those of you who have not been able to launch your notebook so far, we now have the reservation working. So when you're at that home screen and you start your server, click on advanced options, and then you can type HPC _ Python, where the HPC is capitalized and Python is lowercase, and it should work now. Thanks, Rafael. So let's just wait a minute and see if those who have been waiting for that to work.
For the rest, well,
okay, I think you can continue.
Yeah,
continue.
When you manage to run the notebook, go here to NumPy and open this one, 01, array internals, and go through the notebook. And there are some questions, and try to read the questions and try to guess first what is the strides, and then check with the X strides to see if your answer was fine. And then the second part is try to guess from the operation and what you know about the strides, if you are changing memory with these operations here, or we are just changing the metadata. Okay, I'm going to give you 5 minutes. I'm going to mute myself and then ask questions if you need, and then I come back and we discuss the results. Okay.
Okay, there's a question from Hannes. How can I shut down the Jupyter server to be able to restart it? Because you always end up getting the lab view. So what you can do is you can go to File and then click Hub Control Panel. And then it's something like Stop My Server or similar. And then it will ask you again to, are you sure you want to stop the server? And you can click yes. And then it should take you in a little bit of time back to the launcher page. And then you can relaunch using the dedicated reservation. So I've seen that you are currently restarting. So just give it a couple of moments, Hannes, to for the scheduler to be able to schedule you the job. And it should come up pretty soon. Hopefully it should either be at the point where it's saying job running, waiting to connect, or it has already come up. If it's already come up and it's working, give us a thumbs up. Great. Awesome. Thanks, Hannes.
Okay, let's going to share again, if I manage. Okay, let's have a look together to the notebook. There was a question. I just lost it when I shared, but I think it has to do. Okay, we'll go back to it. So we run on this first one. The stride as a demo is 4.1. This is the same example that we had on the presentation. Okay. So now we reshape it to 2.8. The stride is 8.1. If we print it here, we see here that to move in this direction, we move so we need to move 8 bytes, and to move in this direction we move only 1, so 8.1. Okay. This one we made it a line 16.1. Here this is, I think, that was the question. So this is a line, but and then the stride that we get was I forgot. (16.1). So if we here we had the shape is 116, but now if we do like this, there is only 1, and I think which is at the end the same memory. The difference is because anyway the other, we have 16 components in one direction that they move one by one. In the other one, I think he put some default value, because always this index is going to be 0 because there's only one row, and then it doesn't matter what you put here. So that's why you get, I think, this is my interpretation, 16 here, and then when you do this one, you get only 1. Okay. And this one is similar to the first one. The only difference is that we use int 16. Now it's pretty much the same of this, but instead of moving one int 8, he has to move always twice because we increases the size, and that's why we get 8,2. Okay. So we move on to the pieces. If you have more questions, we're going to move on. But if you have more questions, you can copy there, and we can discuss it later. So the next one, we have this operation. We print here. We create X. We print it. It's 0, 1, 2, 3, 4, and then Y we say is equal to Ravel of this one. Ravel, what it does is to give you a flattened array. It's already flattened, but it's what it does. And then when we print again, we change Y, not X, and we see that X changed. So what happened here? So the question is, the problem is that Ravel clearly is just changing the metadata, not changing the memory. And since the metadata is changed, the memory itself is the same. When you change the memory for Y, which is sharing memory with X, then the memory for X, which is the same, is going to change too. Okay. Now, if we use a different one, flatten, we see that it doesn't happen. And the difference is because flatten is changing memory. So this Y is a different, has a different memory buffer than X. Here it doesn't matter because it's a very small array. It's faster any way we do it. But when you have something more heavier, more computational expensive, it's important that you know which functions are using, and try to use solutions that are faster, because sometimes there are always different ways to do things, and this is a kind of reasoning that you can apply for those cases. Okay. Now, if we continue, we create this bigger array, 5,000 by 5,000, and we have 3 operations. This one does a transpose and a Ravel. Ravel, we know already that doesn't change the data buffer. It's just a metadata, and effectively you see here is nanoseconds what it takes. It's very fast. Now we do with this one. Here we are going to expect that it's slower, because flatten, we know that it changes memory. Changing memory is always slower than well, than not changing memory, of course. I wonder why it's so slow. Well, I guess it's time it is running. It automatically runs many times. No? So here we see 16.1 milliseconds. Of course, what we're expecting. And now we have the same operations here, but we don't have X transpose and then X travel. We have the transpose and then the Ravel. And when we run this, let's see what happened. It's slower than this one. Somebody would like to write on the chat? Well, no, I cannot see it anyway. I'm sorry. I'm going to say the answer. The answer is that Ravel, so Ravel, we know it doesn't change memory, but if you do a transpose and then you try to apply Ravel, there is no way, considering the Ravel is to the new order of the transpose, changing metadata, it's not possible to do a Ravel with the current order of the current order of the array. So this one changed the order, and Ravel now he finds out that, okay, if I change the metadata, I cannot do this operation. I have to change memory. Then it automatically will change the memory. So it takes more time than flatten, because, well, probably it's a different algorithm. But here, a function that is changing that is changing always metadata is changing memory, and this is something that you also have to take in account in your real code, because sometimes how the functions operate depends on the situation. Okay. Okay, we're going to move on to the next example. So the next thing that I want to show you is broadcasting. So we are building to our real example. Okay. Broadcasting is something very important in NumPy that has to do with operations that involve arrays of different shapes. So if you sum an n by 1 by n by 1, the sum is going to be element by element, and you will get an n by 1 array. But if you sum an n by 1 by n, something different is going to happen. What's going to happen is that for each of these elements of the array, they are going to be summed by the whole horizontal array. Okay, so here you will get an array repeat, and one of them summed by each of this. So you get for the first row y0 plus x0, y0 plus x1, y0 plus xn, and the same is going to happen by all the in all the rows. Okay, and then at the end you will get an n by n array. So this one here is easy to understand, but it can get a bit complicated when the array has more than 2 dimensions. And now we have an example notebook for that. So let's go now back to the notebook and do and run it. Is 002 broadcasting. The idea of this notebook is there are different situations, and you have to understand each of them, what is happening. So I'm going to give you 5 minutes, maybe a bit less. Just go through the notebook, read the text, please, and try to understand how this broadcasting operation happened. Okay, and then we're going to discuss it. Okay, let's discuss a bit the solution. So here we try to understand the broadcasting starting from the simplest form, which is an array plus a scalar. Okay, here what is going to happen is every element of the array is going to be summed by the scalar, creating an array of the same size. Okay, let's continue. Here we can do it. Now, there is something before continuing to the rest that is creating new dimensions of array. So this array is called linear something. It's a vector, but it doesn't have the notion of horizontal row or column or row or column. So it's 5, but this 5 is not clear what it is. You can add using NP new axis. You can add a new axis to it, and you can convert it in a 5, this line, to a 5.1, which is if we print it, what we see is that we have 5 columns, 5 rows of a single column. It's more or less what is happening here. 5 rows of a single column. And now we gave to our array a notion of row and column. So this one is a column. It's a single column, let's say, with 5 rows. Okay. The next one, we will do something similar, but instead of using NP new axis, creating it on the second here, we create it on the first. Which this means that if we print it, we are going to have one row, single row, that has 5 columns, and this is 1, 5. Okay, single row, 5 column, and 5 rows, single column. What happens when we sum them is what we saw before in the example. For every of these elements here, each of them is going to be added by the array. You will have a plus a, b plus b, a plus b, and so on. And this one will create an horizontal array, horizontal a row of this size, and repeat it for each of them. So you have a 1.5, 1,5, and a 5,1, and you will get a 5,5. Okay. So we can do it here, 5,5. Okay. Now it gets a bit complicated here. If the shape is not only bidimensional, it's three-dimensional. Let's say this is the same thing that here, but now let's say that A has a new dimension in the axis that go inside the screen. Okay, so there are I put 3 inside the screen. So now, and this one is going to have the same 3 dimensions, A1, A2, A3 inside the screen. So each of them are vector. So now we will have 1, which means 1 row of 5 columns, and 5 columns are vectors of 3 dimensions. Okay. Same here. Here we have 5 rows And in every row, there is a single column of elements of 3. So they are like inside of the screen. When you sum this, the sum is going to be exactly like this one, but you will get a third dimension in the axis that go inside the screen. Okay. So we get 5 by 5 by the other 3 inside the screen. Is it clear? Now I can see. Okay. How is using appearance different from reshape? Okay, let's try it. So we have this one that is shape 5. Dot reshape, and we do what we was 5.1, right? It's the same. The result is the same. Now I have to check. I come back to you because I don't know memory-wise what happens if this one returns a new array or only changes the metadata. This one only will change the metadata. We can have a look here quickly. We say v equal reshape, the same operation we did before, and we say v0 equal 22, and then we print x again. Okay, it doesn't change the data. Okay, was it clear this? So we changed the new variable, and we modify the memory of the initial one. So I guess it's pretty much the same. Let's see if we can add more variables. Yeah, it is. Reshape, of course, is more powerful, no? If this is a 6, we can reshape it in 3 and 2. We cannot do that with the new axis, no? So this one is more powerful, does more stuff. Is it clear? Okay. Jonathan is explaining that reshape changes in memory if it's not possible to do it with the metadata, same as we saw with the transpose. Okay, thank you, Jonathan. Answer live. Now you can see he's done. Okay, great. And the second question. Does the operation allocate new memory, or could it be performed by only changing? This is more or less what I did here with the reshape. The idea is that there are other ways to see it, but the way I show now that you can repeat is you get this x here and you assign it to something else, to v. Oh, you assign it to something else, to v, and then you do the same thing I did here. You change v. Let's put another number. Oh, I have no idea what I'm doing wrong here. Sorry, I had a shape. Okay, so it changes the data. This is a simple way that you can see that it changes the metadata. Okay, And also, without doing that, it depends, of course, on the implementation, but it can be, it's something that you don't need the creating a new dimension. You don't need to change the data, because the order of the data or the elements, nothing changed. It's just the way you're going to read it. Okay. Thank you, Francesco. Okay. And here it's the same thing that we saw already. If we start from a no dimensional one, so from a two-dimensional n by 3, n by 3, and we want to obtain this matrix, all the combinations of rows and columns, the subtraction of the combinations of the rows. Sorry, how we do it? So we try to convert this array here to this. So we do two things. We convert one in this shape that we did here, and the other one in this shape that we saw here. And now this operation we already know is going to, when you sum this one, we subtract this one and this one, so these two, it will give you the operation that you want. Okay. Now in the next session we can play. We're going to reuse this thing with a new example. There are questions. Do you have shape? No. This one, I hope I answered it was clear. And this one you already said. I'm sorry, I don't understand the question. Can you do only the shape of the output? Yes, but today later we are going to learn a bit about this case with Dask. If you have a big array and you want to change to get a shape, you have to compute it. You have to get the solution, the output. But later with Dask, we will learn that you don't have it. But depending on which operation are you doing. Okay. So now it's fine. We're going to move. Let's move to the next point. The next point is vectorization. So what is vectorization? Vectorization is when you do operations on the whole array instead of a single element by element. No? For instance, if those x and y are two arrays with some dimension, if you multiply them element by element, this is going to be element by element, but in a single line of code. This is vectorized code. No? So you are multiplying vectors. This is the way you are supposed to run a NumPy code. In NumPy, you're not supposed to do for loops over the arrays. It gives you the support for vectorized operations on the whole array completely. This one is very simple, no? But in general, on more complicated things, you have to use it vectorized to be able to get the most of NumPy. Also, in NumPy, there is something called ufuncs, which means universal functions. Those are functions like this one, like exponential. It's functions that you give an array of certain dimension, and it gives you do some operation and returns an array of the same size. This is again a vectorized operation, and in NumPy you have to use the functions like this. This is how you get advantage of NumPy. Or there are functions that are not ufuncs, but they are also vectorized, like dot. Dot, for instance, you pass two arrays, and it gives you a scalar. But you are doing in a single line operations over the whole array. Although here is a bit different, of course, because you need the whole array to get the final number. But the point is that you never do loops. And the final point is again the same two, but this try to find to vectorize code, try to find math tricks or tools or whatever, changes you can do in your algorithm. So you use these two things. Sometimes it's more obvious to do a for loop, but you really need to change your approach to adapt your data, your problem to be solved with what NumPy gives you. This is the only way you can get speed with NumPy. And now we're going to see an example to show exactly that. And this is the problem that I said before that we're going to run the whole day. We're going to compute the distance matrix, which the distance matrix is a function that you give to arrays, right? This arrays is you can see it as a column, as a n rows of vectors. No, this is a 3-dimensional vector, another one. Here the same, and you want in your matrix all the combinations of them, and you're going to compute the distance. So here we use Euclidean distance, and we want all the combinations. This is that we're going to get these two, and we're going to put it here. Then these two, we're going to put it here, and so on. Then we move to the next row, and we do the same operation, and like that we have all the combinations of distances. Okay. Euclidean distance is from geometry we know in the dimension in this 2-dimensional case is a straight line from one point to another one. We're going to do this exercise also with the city block distance, which is also known as Manhattan distance, which is city block is because it goes through the block of a city. No, you don't go directly, you don't go in straight line, but you kind of go around a block. This the question is the formula is like this: is the abs instead of the Euclidean norm is the subtraction and then the abs. This one will give you this operation here. We're going to do these two problems, and we're going to work on them the whole day. So, I already said that in NumPy we don't use loops because loops in Python are slow, and NumPy gives you the support to give vectorial operation. So this one, the 3 points that we put, it doesn't do operations over the whole arrays. Here we use a NumPy function dot, but this one, okay, is fast, but once you have loops, your whole function is going to be slow. And the last point, we didn't do any effort to change the algorithm to use what NumPy gives. Here, the most obvious thing is to do the combination of rows by for loops, and this is what we did. What would be a good NumPy solution is the following. First, we use a math trick that this Euclidean distance allows to do. Euclidean distance is a formula for I is every row and k is the column. So this is the n by 3. So each of them you can write it like this by the scalar product, and the scalar product of these two things you can write it like this, right? And the good thing now with this trick that we did here, every of these things, of these elements, we can compute it with NumPy. There is something in NumPy that is vectorized and fast that we can use to compute these terms. Okay. The first one, the simplest one, is the dot product. If you have used it, give you the scalar product. But if you put matrices, and then we're going to change here something to make it to look like a matrix, it will give you the matrix product of x and y. So x here, to make it like that, we use it. Sorry, I'm sorry. This is a vector. This is the n by 3, and this is the n by 3. We do it transpose, and then we have the matrix product of the whole vector x and the vector y. And here we already got this part. Okay. The next two, they are the same, but it's not really like this one that we made it a matrix multiplication. This one, you see this ij, and this one is ii and jj. So they are element by element. For that, we can use the function einsum. So einsum, we're going to see now in the notebook. Well, probably after lunch. We're going to see in the notebook that it is the Einstein summation. Is kind of a operation that it means that you're running a sum of these arrays by the elements that are repeated. So here we have a sum over I in Einstein sum and j, but since we have this arrow here, it means don't sum or don't sum over the one that has the arrow. So we are going to sum only over j. Again, you have time to play with it, and like this we can get the missing elements. Then the next thing is just to make it to adapt the shapes so we can zoom it in the way we want. And finally, we can write a function like this. So we do the two einsums, we change the shapes here, adding new axes, we compute the other term, and at the end we sum all of this. And then we put an abs here just because you have a minus, and since so this representation is not exact, you may get very tiny negative numbers that are just artifacts. We want those are effectively zero. So we put it as an abs. And now we can go to the notebook and try to understand what I just explained. We are going to Euclidean distance matrix NumPy, and we are going to go over it. And then there is every byte or every bit of code that I showed here is explained one by one, and I think you can understand better how every part works. So this is the function. Sorry, this is the function that we already discussed, and this is another extra implementation that is also NumPy compliant, and it's also fast. And we're going to compare these two different implementations in NumPy. I think now, if you have questions, we have 4 minutes before the lunch break, and just go or start going over the notebook. And at 1, we're a bit, I'm sorry, we're a bit late, but in the next session we will get 10 minutes, and we can have a look to discuss this notebook. Okay.